Hey guys, welcome back to the channel. If you're new here, I'm Christopher Alix, a college student just trying to survive one coffee fueled assignment at a time. And today, I've got my awesome group with me. Jeruzel Carpio, Adiam, Marlon Delizo, and Franz Perez. Together, we're tackling something pretty interesting. Something that blends math, probability, and a little bit of chaos. This is Activity 6, Random Walk, a model of fluctuations over time. It might sound complicated, but it's actually one of the simplest ways to simulate randomness and understand something called a stochastic process. So, here's the gist. Every flip of the coin determines whether you take a step forward or backward on a one-dimensional number line. Heads, step forward. Tails, step back. Do this enough times and you'll start to see a random path, or a random walk, form over time. Random walks aren't just a classroom activity either. They actually help model real-world phenomena like how stock prices move, how molecules drift, or how trends rise and fall. It's a basic idea that powers a lot of complex systems. The main goal here is to get hands-on with randomness. By simulating a simple random walk, we can better understand the nature of unpredictable systems, how they drift, fluctuate, and sometimes surprise us. And with that intro out of the way, let's move on to the next part, the methodology, which will be explained by Mr. Franz. Stay tuned!
Good day, my name is Franz Perez and we're gonna go through the methodology of our simulated program. So here is the one-dimensional random walk pseudocode and we're gonna have a line-by-line explanation. So first, we initialize position at 0. So we start at the position 0 on a number line, which is the origin, since this is the starting point in the one-dimensional space. We then initialize steps, which are the total number of steps to simulate. So this sets up how many steps the random walk will take. For example, if steps equals 1000, the simulation will take 1000 steps. Now to simulate the coin flips we're gonna use a for loop. So for I from 1 to the steps we do, we perform the following logics with the steps number of times. We generate a random number r between 0 and 1. This simulates randomness. Since 0.5 divides the interval evenly, it gives us a 50% chance to go left or right, just like in a coin flip, heads or tails. So if r is less than 0.5, then we take a step to the left, which is the negative direction. And we perform that by taking the position and subtracting 1, which moves 1 unit to the left on the number line. Else, we use the position plus 1, which takes a step to the right, which is the positive direction. We then use the N4 where we repeat the process for all the steps. Finally, we output the final position. So after all the steps are taken, we report the final location on the number line. This will be positive, negative, or 0 depending on the random path. Next, we're gonna discuss the flowchart. Here we have a detailed visual flowchart for the random walk simulation program that we've created. Here is a detailed breakdown of the main program flow. First, of course, we have the start where the program begins execution. We then proceed to the display main menu, which presents the user with 6 options. And here we have the user choice decision, where the branches based on the menu selection. Of course, for option 6, if they choose that option, it will exit the program and end it. But if they choose the options 1 to 4, we have the interactive simulations. So for interactive simulation branch, we have the steps for running a single random walk simulation. So first, we have the run simulation, which starts the interactive simulation with selected parameters. We then proceed with the individual simulation box, which initializes the position to 0. We then flip a coin to determine movement direction, which is either positive 1 or negative 1 or right or left. We then update the position based on the coin flip and then display the current results and the visualization. After that, we return to the main menu after the completion. And then for the comparison branch or the option 5, here we're gonna run multiple random walks comparison which features the following steps. First, we get the parameters, which collects the user inputs for the number of steps, the seeds, and the labels. We then proceed with the random walk comparison. We first generate 3 separate random walks. We then calculate the statistics for each walk. After that, we save the trajectory data to a CSV file, and with that CSV file, we generate a matplotlib comparison plot. We then display the comprehensive results. After that, we return to the main menu after the analysis is complete. So this visualization helps us to understand the program flow and how the various components interact. And this flowchart clearly shows how the program is structured around the individual simulations and comparative analysis.
Hi everyone, I'm Jeruzel Carpio, and today I'll show you this simple Python program about random walk simulation. So this program flips a coin to decide if we move left or right. That's what we call a random walk. So now let's run it. So here's our program. So our program has a lot of options, but let's run number 1, which has the default settings of 50 steps to take. So we start at 0 on this number line. So every time I press enter, the program flips a coin and moves us. So let's try it. So the program flipped a coin and got heads, which means we're currently at position 1. So because heads means go right and tails means go left, or heads means +1 in the number line, meanwhile tails means -1. So let's try yet another. So we get tails and we go back to 0. So let's look at this. The arrow head here, or the triangle, shows us where we are at right now. The O or 0 symbol is where we started. So let's take another step. So the dots under the number line shows us the path or the places we've been. So let's keep pressing enter and watch each step. So we're currently at step 40 and position 6. So it's pretty neat how we moved to position 6, right? So now let's keep going. We're almost done. And that's it. So let's check out what happened. So we ended at the final position of 6, the number line. So the part is right. We bridge is 10, and the farthest left we bridge is -4. And this is the path we taken. So that's all for our basic simulation. Now I'd like to hand over to Miss Adiam, who will run 3 simulations side by side and shows us how they compare. Thank you.
So hi, I'm Christine Adiam, and I'll be running again a random walk simulator and will later compare and analyze the results. So first, we are greeted again by the welcome screen random walk, a model of fluctuations over time, so we'll just press enter to continue. Now we're at the main menu. To generate the comparison plot, we need to choose option 5, where we are going to compare 3 random walks with graph, so we'll just type 5 and press enter. The simulation now asks for the parameters for these walks. So first, enter number of steps for each walk. For the visualization we're about to discuss, this was set to 50, so we just type 50 and press enter. Next, would you like to set seeds for reproducibility? To get the specific random outcome that matches our discussion, we would have either used specific seeds or, as in many demonstrations, we might select N for no to see a fresh random outcome. For the purpose of this specific explanation we're about to give, let's assume that the plot we're looking at is the result of such a run where no specific seeds were preset, or that we use seeds that produce the exact plot described. So we type N and press enter. Then, would you like to set custom labels for each walk? The plot uses the default labels walk 1, walk 2, and walk 3, so we'll choose N for no here as well and press enter. So now the program generates the 3 random walks, calculates their statistics, saves the data, and then the plot window appears. Okay, now that we have our plot displayed, let's analyze what this specific visualization is showing us. So this simulation visualizes 3 independent 50-step random walks labeled Walk 1 as blue, Walk 2 as orange, and Walk 3 as green. And their outcomes, final positions of -2 for walk 1, +6 for walk 2, and -8 for walk 3 in this specific run, are consistent with the probability theory predicts. Specifically, their final positions and the overall spread of their paths are well within the expected range around a theoretical average endpoint of 0, with the typical deviation from this average being about 7.07 steps, the standard deviation. The most significant insight you'll observe from the plot is the inherent variability and unpredictability in random processes. Even though each walk follows the exact same simple rules, an equal chance of moving one step forward or backward at each point. Each generates a completely unique trajectory. You'll likely see these paths drift away from the starting point for periods, purely due to the cumulative effect of random choices, not because of any underlying bias. While some walks exhibit significant features such as walk 3, the green line, dipping notably to -12, or walk 3, the orange line, reaching a peak of +7. These are not statistical oddities but rather typical examples of the random fluctuations expected in such a limited number of steps, confirming the system behaved as anticipated without any underlying anomalies deviating from the theoretical random behavior. That's all for my part, thank you.
So, what did we really learn from this random walk simulation? At first glance, it might just look like a simple game of flipping a coin and moving left or right. But what it actually shows us is a powerful idea in probability. Even when you follow the exact same rules, randomness alone can produce totally different results. This randomness is everywhere, from stock market prices to molecule movements in science, to decisions made by algorithms. And understanding that random doesn't mean patternless or chaotic is key. So, what's the big takeaway? Even simple rules, when repeated over time with randomness, can lead to surprisingly complex and varied behavior. And that's why simulations like this aren't just fun, they're also a great way to see probability in action. Thank you.